Those of you standing in the back, there's some open seats, so by all means, you're welcome to come and take a seat. Our operating system of the day is BSD, and that's one that I'm going to imagine a great number of you have probably heard of, as opposed to most of those that we have actually been talking about. BSD actually goes back pretty far. It was originally released in 1978, and it originally was not an operating system, which is kind of an interesting thing. So it was really just meant to be an extension to Unix version 6. And they called it 1BSD, and really they had done a bunch of Pascal educational software tools. It included an editor called EX. It had a shell, a bunch of new shell commands, and a game. And they packaged it up and they shipped it out to people with Unix version 6, and there you go. Of course, it was quite popular, and so they released 2BSD, which included, of course, the wonderful VI, which everybody should use, right? None of that Emacs stuff around here. And it also included something called C shell, not the C shell you were exposed to in CS136. That's, yeah, we won't talk about that. All right. Then it was, again, with that additional release of 2BSD, it started being even more popular. Wow, look at this great editor. Everybody loves it. Look at this shell program. It's great. And so 3BSD, with significant funding from DARPA down in the United States, you know, that's the big league funding down there for computing equipment and software, it actually turned into its own operating system. And they originally weren't going to call it BSD. They were thinking about calling it VM Unix instead, which doesn't have the same ring to it. The reason for VM is virtual memory, because this particular version of BSD actually offered a very wonderful implementation of virtual memory for VAX machines, which is a kind of hardware that doesn't exist anymore. Yeah, and it kind of took off from there. For example, some of the features they've added in later versions, it's the first Unix-like operating system with internet protocol stacks. Sockets, that's a really big thing. Sockets are the process-to-process communication tools, or it's one of the things that we have to let processes talk to each other. Yeah, came from BSD. That's kind of fun. And it's actually most of the Unix-based operating systems that you use that are not Linux are actually coming from BSD. So if you have a Mac, you actually have the grandchild of BSD in front of you. If you're using Solaris, which I'm not imagining any of you are, but that's also a BSD, and there's FreeBSD and NetBSD, and there's so many variants of it. And of course, people started making awesome logos for their OS. So it's got a cute little demon here, which is fun. All right. So I know it's been like 10 days or so since you thought about this course, so you've probably forgotten everything. Before we get back into talking about virtual memory, just a few things I want you to keep in mind. Of course, A2A is due this week, so you might want to get on that. The quiz that I thought was last Friday is this Friday. And yes, I updated Learn to reflect that fact, so please pay attention to that. It covers up to and including everything we covered before reading week, so all the stuff you've forgotten, right? And then you have a midterm that is next week on the 30th, and we will do midterm review in class on the Tuesday before. There's not going to be a formal review session, but we will do in-class review. If there's any particular topics you do want to see in that review, please do send me an email and I will see about including it. The midterm is probably going to cover up to and including paging, which we're going to be covering today. So single level paging and multi-level paging, those are totally fair game. When you're preparing for your midterm, and I hope that you have some time, if you haven't already, to start preparing for your midterm, remember that the course website actually has all of the previous midterms and all of their solutions posted, with the exception of the few most recent, in which we will actually post those to Piazza. We just haven't gotten around to getting them on the website yet. The other thing to give you a heads up about is that obviously following A2A, there's A2B, and we will be covering how to implement A2B in Thursday of next week. So I think that's Halloween actually. We'll go over A2B. I don't know, that might make you terrified, or it might make you think, oh, this will be easy, right? I don't know. All right. So one more thing I wanted to have some fun talking about is one of the big themes in this course is talking about how operating systems are abstracting things like hardware from the user programs, and their implementation of the operating system itself is abstracted from the user programs. And something happened very recently that is a good example as to why this abstraction is very, very important, and I thought it would be interesting to share it with you. So how many of you are Mac people? How many of you then updated to Catalina? Quite a few here? Anything break? So, interesting story. The tool which we are using to stream this lecture doesn't work in Catalina. When they made the upgrade to Catalina, they actually changed how permissions for certain devices work. And the OBS software, it's Open Broadcast something, I don't know what it stands for. It had some assumptions based on how permissions for particular devices had to be done. And when you upgraded to Catalina, OBS's mechanism for acquiring permission to use your camera and your microphone and grab the screen capture, broken. We are still streaming. It's not completely functioning. We don't have display capture, but we've got the video kind of hacked back together. But I just thought it's an interesting thing to know that sometimes when we actually make big upgrades to our operating system, some of the big changes, if we haven't abstracted these things sufficiently from the user program, can actually cause the user programs to just not work. And that's not the only one that doesn't work for me. So another thing that Catalina did was they have officially discontinued support for 32-bit applications in macOS. One of the #1 applications I use is 32-bit only. And now I'm sitting here, I was trying to open it up last night. It's a stereo photo program, and I'm sitting, why is this not opening? And it's like, oh, it's 32 bits. This is why OS abstraction is really, really important. Also, to be fair, that program's 10 years old, but. All right, so going back to where we were then. Hopefully I've scared you enough to wait to upgrade to Catalina if you haven't already. We left off looking at virtual memory, and if you remember, what we are doing is we are trying to abstract where a process actually lives in RAM from the process itself. So the process thinks it lives in addresses 0 to the end of RAM, except that's completely fake. And the process isn't even aware of it. Where they actually live is only known by the operating system. Now, that abstraction gives us a lot of wonderful things. It is a security mechanism. Because if we did know where we lived in physical memory, then we, by virtue of knowing where we are, we know where we are not. And I can write a very quick little program that does an array out of bounds, and I can just steal data from somebody else. Just like that. So obviously, we don't want processes really know where they live, because it gives us very easy access to stealing data from everybody else. So virtual memory is a big part of providing process isolation. Another thing that we get from virtual memory is we get the ability to have process address spaces not always loaded into physical memory at the same time. It actually lets us have more processes running than our physical memory can actually support. So I can have 10 copies of MATLAB open, each with a 5 gigabyte address space. Sorry, I really like to pick on MATLAB because it's ridiculous. And I can have 5 of them open. That's 25 gigs of RAM I would need. And I can have, on top of that, I can have 10,000 Chrome windows open, each at 2 gigs of RAM, and yet it still works. And I only have 32 gigs of RAM in this machine. And it works because through virtual memory, we've actually, and we're going to see this today, how it would kind of happen, is we have the ability to only have the region of the address space we are using right now actually loaded into physical memory, and everything else stored elsewhere. Which means that we can actually run more processes than our physical capabilities would suggest we are actually able to do. So virtual memory is a really big thing. Now we looked at last class, dynamic relocation, just to refresh you. Let's go back in time here. Here we are. We make the assumption that our address spaces are actually contiguous in virtual memory, and we are going to find a corresponding equal size block of physical memory that maps to that virtual memory, and it must be contiguous. We can't break it apart. And then to do the translation, we keep track of where the start of that block is in physical memory and how big it is. And then to go from virtual back to physical, we just add the offset. And to go from physical to virtual, we subtract the offset. That's it. Now, it's wonderfully simple and efficient, which is one of those things that we really love, but unfortunately, dynamic relocation suffered from reality. And the reality is, if we look at how an address space is laid out, it's not one contiguous block of virtual memory. We have a code segment, and then we have a data segment and a stack segment, and they're all spaced quite far apart. And so from dynamic relocation's perspective, because we have to have one contiguous block of memory, in OS 161 at least, every single process would require a 2 gigabyte chunk of RAM, which means we have a significant amount of internal fragmentation going on, wasted space, decreased ability to run processes at the same time because they all have to be right there in RAM. Yeah, this is not good. Nobody does this. So we solved this problem by doing segmentation. We noted the fact that looking at our address space layout, there are distinct segments that we do use. So why don't we just do dynamic relocation on the individual segments? So we divided our address into 2 parts. We now have the highest order bits indicating which segment it is, and the remaining bits of the address are going to be the position within that segment that we are at. Yes?
So how do you compute that 1.2 megabyte figure for the sort program?
So that 1.2 megabytes, so that's the sort program in OS 161. And that's if we take the amount of space we get for the code segment, the data segment, and the stack, it would sum to 1.2 megabytes. And the reason why we can calculate that is the binary file itself tells us how big the code and data segment are, and because the compiler knows. And the other thing is the stack segment is actually has its size dictated by the operating system. And it's 48 kilobytes in OS 161. Yeah, so we can actually calculate that. All right, so what we did then with segmentation is instead of taking the whole block, we're just going to map each of the individual segments themselves. So I've got, in this example, we have just 2 segments. So I grab segment 0, I find a contiguous block of physical memory for segment 0. And then I have segment 1, and I find a contiguous block anywhere I can for segment 1, and the same for process B. And then for each of those segments, I keep track of the offset and the limit. And now when I do address translation, I have to first extract the highest order bits to figure out which segment this is, and then using the remainder of the virtual address that tells me the offset within the segment, I then add the relocation compared to the limit. We're done. And this is great. This is just as easy as dynamic relocation. We only need to store a couple extra integers because realistically speaking, your address space doesn't have 500 segments. Address spaces have a code segment, a read-only segment, which in OS 161 is actually just a part of the code segment. Because code is also read-only, so why separate them? Then we have the globals, and the heap, and the stack. There's not that many segments. So the number of integers we actually have to keep around in the operating system to support this implementation of virtual memory is actually not that much. It's really, really great. The other added advantage is we have no internal fragmentation. We're only ever allocating physical memory that we are actually going to use for the individual segments. Unfortunately, segmentation has an external fragmentation problem because each of the allocations of physical memory are differently sized. Some of them are going to be 10 megs and some of them are going to be 12 kilobytes. And the problem with that is you may, as a whole, have that amount of space free in physical memory, but if it's not contiguous, segmentation can't use it. Now you might be like, well, in 241 we learned about, methods for defragging memory. Why can't I use one of those technologies? Well, here's why. Because they're slow. Because you're telling me I'm going to pause the operation of my program so that you can reorder 64 gigs of RAM? That doesn't make any sense. I don't know about you, but if it takes more than 3 seconds for my computer to do anything, I'm going to throw it out the window. You don't want to put an extra delay on the users. Now, that being said, segmentation is absolutely used. And it has been used in many operating systems in the past, and it actually is a really old idea. It actually goes back to the 1950s. It's also what OS 161 uses. Now, we had talked about a method where the MMU, remember that is the piece on the CPU that's responsible for actually performing the address translations, would need a relocation and limit register for each of the segments. The problem, of course, is that each time you add registers to hardware, you're actually changing the size of the hardware. Hardware space is a premium, and you don't want to take all that extra space just so you can have registers for each and every segment. And so how you actually usually see segmentation implemented in hardware is instead our MMU has just 2 registers. Not 2 per segment, just 2 registers. One register will hold how many segments are actually in the address space, and the other register holds a pointer to what's known as a segment table. And when the address is received by the MMU, we are going to extract the segment bits. We check to make sure it's a valid segment number. So it's totally possible your address space has 3 segments and you just got an address for segment 9. That you got to be able to fail, right? If it's a failure, then you're going to throw an exception. And if not, we'll use the index, let's say it's index 3, to index our segment table. And in the segment table entry, it will tell us the relocation value, the limit value, and a bunch of other information that we really, really need. Like, is this segment read-only or not? Our previous implementation with registers never even considered the fact that the code segment should be read-only. So with the segment table approach, we can actually store a lot more information with less hardware space, and you'll see this is actually much more common. Is this how OS 161 does it? No. OS 161's implementation of virtual memory is called dumb for a reason. It's also why you have assignment 3. It's called you're going to make it not so dumb. Yeah.
So is the segment table stored in RAM, or is it on?
The segment table is stored in RAM, yes. All right. Yeah.
Is it a fixed size every time?
So a fixed size every time. There is going to be a limitation on how big it can be, because the MMU is going to say, I am going to use X bits for my segment number and Y bits for the segment offset. But whether your process uses all of the available segments, it doesn't have to. But there is a physical maximum that we can have. And that's a hardware spec. All right. So we could take this further. One of the problems, like I said, with segmentation is this issue of fragmentation. Segmentation is a really good method, but it still suffers from fragmentation. How do we get rid of that? Well, the problem with that creates the fragmentation is the fact that every single allocation we do is a different size. How could we make it so that every single allocation we do is the same size? Because if every allocation is the same size, there's no external fragmentation. But of course, if every allocation is the same size, then wait a minute. Well, not everything I do is the same size, so I'd be wasting some kind of internal space. So the trick is, how can I break it down such that I'm doing not too big equal-sized allocations, but not too small either? What's a good balance to solve the fragmentation problem? And that's actually the next implementation of virtual memory. It's called paging. And I'm pretty sure you probably remember some of this from 251. If you did promptly forget the course, 2 seconds after the exam. I love that course. That textbook by Hennessy and Patterson, I don't know if you bought it, I don't know if you've cracked it open, but if you're bored someday, read it. It's actually a really well-written book. And yes, I know it's ridiculously expensive, but it's also a really good book. All right, so what we're going to do for paging is first we're going to take our physical memory and we are going to logically, that means in code, divide our physical memory into equal sized frames. Now our frames, most commonly, at least in industry, we set the size to 4 kilobyte, but that doesn't mean they have to be. So if we use 4 kilobyte frames, and in our slides, we're using an 18-bit physical address, which means we have 256 kilobytes of RAM. Then in order to figure out how many frames of physical memory I have, I take the size of physical memory, I divide it by the frame size, and that tells me how many frames there are. So I have 2 to the power of 18 bytes of physical memory. Thing to memorize, 4 kilobytes is also 2 to the power of 12 bytes. So I divide 2 to the 18 by 2 to the 12 gives me 2 to the 6, 64 frames. So now I've logically divided my physical memory. And let's do the same thing with the virtual memory. So we're going to take our virtual memory and we're going to divide it into equally sized pages. And again, this is done programmatically, it's not a physical thing. And those pages are going to be the same size as the frames. So we were using 4 kilobyte frames, so we will use 4 kilobyte pages, which means for our virtual memory in the slides, we're using 16-bit virtual addresses. That's 2 to the, I think that's just 4 kilobytes. I can add. So we've got 2 to the power of 16 bytes. So the number of pages of virtual memory we have is 2 to the 16 divided by 2 to the 12, which gives me 16 pages of virtual memory. We do not have to use all of them. That is just the maximum number of pages there could be. So what do we do now? So we've divided logically both physical memory and virtual memory into these equal sized pages. And now what we get to do is you've got a code segment. And the code segment is 7 pages. All right? So instead of getting 7 contiguous pages of physical memory, why don't I just ask RAM for any 7 pages? And so now my code segment that's 7 pages long, it's got some frames over here, and some frames over there, and some frames wherever they will fit. So we're no longer requiring that the code segment is entirely contiguous in physical memory. We divide it into these pages, and then we map each individual page to whichever frame is available. Now what's really cool about this is that those frames, they don't have to be in RAM. They don't. Technically speaking, I could say this page, you know what, it's not in RAM right now, it's on disk, and here's its address. And this page right here, it's not on disk, it's not even on disk or RAM, it's on a CD drive. I mean, no one would do that, but you could theoretically do it. It's through paging that we get the ability to have more processes running than we have physical memory to support. We'll be talking more about exactly how we do this at the very end of this module, But just as a heads up, this is called on-demand paging. And what we're going to do is when the MMU tries to translate an address, if it's not actually in RAM, we throw an exception and the kernel will load it into RAM for us. So that's really cool. We'll talk more about that later. Now, how does this actually work then? Because with segmentation and dynamic relocation, I had to, for each allocation of physical memory, I had to keep track of the relocation or offset and the limit for all of them. But now I've divided everything into teeny tiny pieces. And I've mapped them, I've just taken those pieces and I've thrown them to the wind in memory. How do I keep track of that? Well, one thing I don't have to keep track of is the page size, the limit. Because every allocation is the same size. So the operating system will have a constant somewhere in it that sets the page size, and it's just one value. We don't have to store it in each and every single page, because they're all the same size. But we do have to keep track of which frame each page maps to. And we do this with the use of a page table. So what we do is we create a page table that has an entry for every single page, regardless of whether we are using it or not. Now, you might be tempted to believe from the example in the slides that, well, I'm only using 7 pages, so my page table only needs to have 7 entries. Well, the address space that was presented in these slides also makes you think that the code, the data, and the stack are all together like this. We know they're not. Code's over here, data's over here, and the stack's all the way over there, which means there are pages in between each of them that are not actually being used. So because of the way address spaces are laid out, our page table actually has to have an entry for every page, regardless of whether we are using it. Then what we're going to do is, in our page table entry, at least version 0 of our page table entries, we will have a frame number that is which frame does this page map to. And we also have a valid bit. The valid bit is 1 if we are actually using this page. The valid bit is 0 if we're not. Not too bad. Now you might be wondering, well, why don't I just let you use the number 0 in the frame field to indicate that this is not being used? Well, unfortunately, 0 is a valid frame. So how would you tell the difference between valid frame and error? And obviously we don't want negative values here, so. Hence the valid bit. It's just 1 bit, it's fine. All right. Now, how many entries are in a page table? Well, the number of entries in the page table is equal to the number of pages of virtual memory there are. So there's a lovely formula here. Number of page table entries is equal to the maximum amount of virtual memory divided by the page size. Yeah?
So is the maximum amount of virtual memory like 2 to the 32 or whatever, like your bits?
Yes, so it's however many bits you are using to address virtual memory, 2 to the power of that number of bits. That's the maximum possible size of virtual memory. All right, so how do we do the magical translation then? Well, first off, what's our MMU going to have? Our MMU only has to have one thing, just one thing. Page table base register, that's it. It is a register that holds the address of the page table in RAM, because that's where this page table is going to be. This page table is going to be stored in RAM. And so our MMU needs to have the address of the page table so it can actually look things up. So that's all our MMU needs is one register. That's pretty awesome. Unfortunately, how we do the translation is a little bit more work. So what we're going to do is we're actually going to take the virtual address, and what we know is that it has 2 parts, just like segmentation. So if this is my virtual address, the higher order bits, just like with segmentation, are going to be used to indicate which page is it. So these bits will be the page number. And the remaining bits are the page offset. Like so. So in order for us to do the translation, what we have to do is extract the bits for the page number. That's going to give us the index into the page table. So we extract the bits for the page number, and then we're going to use that to get a page table entry from our page table. The first thing that we do is we check the valid bit. If the valid bit is 0, we throw an exception. If the valid bit is 1, then we take the frame number and we're going to shove it into the higher order bits with some magic I'll show you in a minute. And then we're going to add the offset, and there's the translated address. We don't have to check the limit. We don't have to do any limit comparisons for this. Now, how do you actually extract the page number and all of that wonderful stuff? Well, first off, we have to ask ourselves, how many bits do we even need for the page number? Well, the number of bits that you need for the page number is the log of the number of page table entries. So however many page table entries there are, take the log of that, and that is the number of bits that you need to index it. So that's fairly straightforward. But now you're the MMU. How are you going to actually get that information out? Well, to get the page number, you are going to take the virtual address and you are going to divide it by the page size. And then to get to the page offset, you're going to take the virtual address and take it modulo the page size. Anyone here want to do division modulo in hex without a calculator? I don't. Don't worry, there's an easier way to do this. So let's look at this in a different way. So if you look at how the address is set up, as I said, it's two parts. Not only is the virtual address two parts, but so is the physical address. The virtual address is page number, page offset. The physical address is frame number, frame offset. The number of bits that we use for the page offset and the frame offset is the same because page and frames are the same size. Those occupy the lower bits. Then whatever is left is used for the page number or the frame number. Now what we're actually doing here is we've calculated that the number of bits we need in this particular example from the slides is 4 bits for our page number. So what we do is we extract the upper 4 bits of the address and we use that to index the page table. And if it's valid, we get the frame number, which is 6 bits, because remember we are using a 16-bit virtual but 18-bit physical addresses, so there's more frames than pages. So we have 6 bits for the frame number. So we get our 6 bits from the table. We shove that into the highest order bits of our physical address, and then the offset, just drop it down. No division, no modulo, nothing like that. Okay.
If you have more physical pages than like virtual pages, then aren't there going to be a bunch of them that you can never access?
Well, there's multiple processes, right? So in our example here, our processes are restricted to 64 kilobyte address spaces, and our physical memory has 256 kilobytes available. So I can actually, it's not that the rest of that physical memory is not being used, it's just that other processes can actually live in memory at the same time. And they can only use the maximum amount. So you can have, I don't know, whatever 256 divided by 64 is. 4 processes using all 64 kilobytes at the same time. That's kind of an uncommon thing, to use 16 and 18. This example here is just because it fits in the slides. Because we can draw it and it actually works. All right. Now, there is a little bit of math you have to do in order to do this method. In order to use this method here, what you need to do is figure out how many bits for the page offset, how many bits for the page number, and how many bits for the frame number. So, there are formulas here on this page, which I think are things you need to memorize and understand how they work. So number of bits for the page offset. The page offset is only related to the size of the page. So you take the log of the page size. That's it. Not too bad. How many page table entries are there? Well, from before, you take the maximum amount of virtual memory. So in the example of these slides, that's 2 to the 16. You divide it by the page size, which in this case is 2 to the 12 or 4 kilobytes, and that gives you 2 to the power of 4. And then the number of bits I need for the page number is the log of 2 to the power 4, which gives me 4 bits. And then to figure out how many bits I need for the frame number, I take the log of the number of frames, which is going to be there 2 to the power of 6 frames. So I need 6 bits per frame. This is easier than trying to do division and modulo in hex. Divide it out, draw it out, take your bits, add it up. Now, you can reassemble your address as I've shown you here, where you take the frame number, drop it into the high bits, take the offset, drop it into the low bits. But the other method to do it is it's actually the frame number multiplied by the frame size or page size, since they're the same, plus the offset. That's the actual formula for computing the physical address for a virtual one here. Frame number times page size plus offset. And that's effectively what you're doing with the other method here. It's just easier because you're not doing division and multiplication with hex. All right, any questions about how that works?
If the page table entry is not valid, will it be loaded into that will it be loaded into memory and then will it try again, knowing that that's where the memory's been put in RAM?
So if the page table entry is not valid,
Not valid, yeah.
so it's invalid.
Yeah, so it is.
So if the page table entry is invalid, then there's no corresponding frame for that region.
Okay.
So we're not even using it.
Okay.
Like we are actually not using it at all. So we never with paging allocate more space than we actually use. Aside from a teeny bit of extra space, maybe your process only uses 1 kilobyte for the code segment and your pages are 4 kilobytes, so you have 3 kilobytes of wasted space. But if you have 32 gigs of RAM, I don't think you care about the 3 kilobytes of wasted space. Yeah.
So if you have your virtual address space being a lot larger than your physical address space, then like what happens, for example, if you already have, let's say you have only 6 bits reserved for your physical frame numbers, and then you already have all of those loaded into RAM, you're going to load a new one. Like what kind of stuff you have to do with the kernel to address?
Okay, so you're asking more about how do we do on-demand paging when the virtual address space is bigger than the amount of physical memory we have. What ends up happening is we'll only load the pages of our address space into RAM when we actually need them. So the MMU will throw an exception when it finds, hey, this isn't here, and there will be an entry in the page table. There's a special flag we add to the page table to indicate not in RAM yet. And when it sees that flag, the MMU throws the exception, and the operating system responds by loading that page that isn't in RAM into RAM. Now, of course, there's a possibility that there's no RAM available. Cache evictions. We have to choose somebody to cache. And again, we'll cover that more at the end of the module. Any other questions about this? All right. Well, why don't you take the next 5 minutes and why don't we have you do the address translations for process A and process B. And then we'll see how you've done. Now you'll note here in our page table there's the ... regions. That means in between the first and the bottom in there, it's all invalid, okay? So take 5 minutes. You can work together, try to translate these few addresses here, right?
The first bit, right? This is where no.
If you're sitting there with your calculator, remember you don't get one on the exam. Because it doesn't matter which process we are translating them for, the page number and the offset will be the same for the virtual address. That's not key. Alright, so what's the page number for our first one here? Anyone want to share? 1. That's correct. And you can just yell it out, by the way. What about page number for this one?
9.
9. And this one here?
0.
All right. Wonderful. Now, word of warning, when it comes down to it, this is a lovely example where the number of bits we use for the page number is a multiple of 4. Don't always expect that. It could be 6 bits, in which case you have to decompose this into binary, extract 6 bits, and then put it all back together again. This one's nice. All right, so what's the offset then of the first one?
2C.
2C. And this one? And this one here?
24.
That's correct. Okay. So, in order to do the address translation, what we would normally do is we would take the frame number, multiply it by the frame size, and add the offset. But before we do that, we need to look up each of these entries in the page table. So how many of you say, for process A, this address is valid? The first one. Does anybody disagree? So I'm not going to do the frame size times the frame number, add the offset, because all I'm going to do is I'm going to look up my frame number. I see it's 26. I know that's going to be the upper bit, so I'm just going to drop that down and add the offset in. So I get 26 and it's valid. So you should get 2602. Pretty easy. All right, how many of you say the second address is valid for process A? How many of you say it's not valid? So what response should you put? Exception. Make sure you say exception. You are human MMUs. You don't know why it doesn't work and you don't care. You see a problem and you say exception. And looking at the last one here, obviously it's also a valid one. We're on page 0, and so we're going to get now, you'll notice here that for numbers like this, there are these leading zeros. Sometimes we drop them to save space, but that doesn't mean they're not there. So pay attention. All right, now, process B. The exact same addresses, and if we look them up, we'll get page 1, there I'm getting 15. So for process B, 1502C. And then page 9, oh, that one's valid, so we get, and then the last one, we get page 0, so that's frame 14. Hopefully, I haven't added too many zeros, but that's, I think I have. Yes. I have a bad habit of adding too many zeros. All right. That's how the translation works. Any questions now? Okay.
How did you get the frame size?
How did I get the frame size? So in this particular example, we are using 18-bit physical addresses, and that means that there are 2 to the power of 6 frames. So we're using 6 bits. The log of the number of frames gives us 6 bits. Now you may be like, but wait a minute, this is 2 hex digits. Wouldn't that technically be 8 bits? But the highest order 2 for all of those frame numbers will always be 0. So that's why that works. Does that make sense? All right. Any other questions about this address translation? All right. Well then, here's the problem. Let's break it down a little bit more. Right now our page table only contains 2 pieces of information, a valid bit and the frame number. And there's actually a lot more information that we'd probably like to convey about each of these pages. For example, code segments should be read-only. If you make a constant global, that should also be read-only. And at the moment, we haven't indicated how that actually happens. And so our page table entries, what we really want to do is include other bits of information to indicate things like, is this a read-only page or not? And so what we'll actually see is a write protection bit in a page table entry. We also have things like the use bit, the dirty bit, the present bit. The use bit is indicating, has this page table entry been used to translate any addresses? We also have a bit called the dirty bit. Has any address translation resulted in memory being written to this particular page? Then we have the present bit. The present bit is saying, is this page a virtual memory in RAM or not? Which is how we do on-demand paging, as we'll see. So page table entries, there is much more to them than just a frame number and a value. There are other bits to indicate various things about usage and read-only and so on and so forth. Now, in this class, we will never ask you to calculate the size of a page table entry. That will always be given to you, but it is usually a power of 2 for the record. All right. So how big is this page table then? Well, in order to figure out the size of the page table, we need to know a few things. We need to know how many page table entries there are. We already know that. And then we need to know what is the size of each of those page table entries, which, as I said, is always going to be provided to you. And then to calculate the total amount of space that that page table occupies, you take the size of the page table entry and you're going to multiply it by the number of entries in the page table. Okay, that's for page tables. So my page tables, for this example in the course notes, well, we have, if we're saying that each page table entry is 32 bits, then hey, I only need 64 bytes to store each page table. Who cares? It's tiny. Well, who uses 16 bits? The last Windows operating system to use 16 bits was Windows 3.1, which I'm pretty sure was before all of your time. So let's look at this. What about if we had 32-bit virtual addresses? How big is the page table size there? Well, we're going to take 32 bits. Let's figure out the number of PTEs. That's going to be 2 to the power of 32 divided by 2 to the 12, because 4 kilobytes is realistically the most common page size. So that means I have a page table with 2 to the power of 20 entries in it. Because remember, you have an entry whether the page is valid or not because of how the address space is laid out. So I've got 2 to the power of 20 entries. Each of those entries is 32 bits. Ooh. That's not looking good all of a sudden. So if my page table entries are 32 bits, I'm now using 2 to the power of 25 bytes per page table. Actually, we end up using 4 megabytes per page table. Still probably doesn't seem that bad, right? That's not that bad. It's really not that bad. But we don't use 32 bits anymore. And in fact, if you have Catalina running on your operating system, you really aren't using 32 bits because it doesn't support it at all. You are realistically using for virtual memory a minimum of 48 bits. Linux right now actually supports up to 57. But if you're using 48 bits for your virtual addresses, then we are using 2 to the power of 38 bytes for the page table. That's 256 gigabytes. And if you have that much RAM, I want to know where you live because your computer's going to disappear. That's ridiculous. We can't have page tables this big. When we think back to the goals of implementing virtual memory, some of the goals were isolation and protection, and it gives us this. But the one thing paging doesn't give us is efficiency. The calculation's not too bad, but the amount of space we need per process in order to store this page table is absolutely ridiculous. This is silly. Because if I have hello world, you're telling me that my 1 kilobyte address space, I need a 256 gigabyte page table for it? That doesn't make any sense. And of course, here's the problem, the real problem. Where do those page tables live again? They live in the kernel's memory. So you can't even boot the operating system? This just doesn't work. So while single level paging is a possibility, as the number of bits increases for our virtual addresses, it just doesn't scale. Doesn't scale at all. All right, how do we fix it? Well, what we want to do is we still really like this idea of paging because it solves our external fragmentation problem. And that's actually a pretty big deal. It also gives us the ability to do on-demand paging, which lets us run more processes than we technically have memory for. So how do we shrink the page table? Well, I want to take you back in time to maybe when you were 5 years old, the first time you started downloading crap off the internet. So I remember you downloaded stuff, and most people download it to the desktop before there was this downloads folder. And so you end up, everybody, you download all this stuff. Oh, look, a cool WAV file. Sorry, that's from when I started using the internet. Oh, Star Wars WAV files, yeah. Bigger than a disk. So you download all these files and you put them all on the desktop. And by the way, I've seen some pretty nasty desktops in my time. There's this one individual I've worked with a few years, and their desktop actually scrolls for 5 pages. They dumped everything onto their desktop. That's single level paging. That's taking every piece of information and dumping it into a single folder. What we want to do now is add some organization. So essentially what we're going to do is, if we're talking about just your disk, you've got one folder with everything in it, and it's got a billion files, wouldn't it be efficient to add, hey, let's add directories by the starting letter of the file name. So a directory for files that start with A, and a directory for files that start with B, a directory for files that start with C, and so on and so forth. And if there's no files on your disk that start with the letter J, then don't make the directory for it. We're going to do the same thing with the page table. We're going to turn it into a tree. And we are not, if there are no valid pages in that sub-page table, do not make the table for it. And so now we will still have page tables that have invalid entries in them, but on average, there will be significantly fewer. And the page table itself, on average, will be significantly smaller than its single level counterpart. So what we are doing is we have a level 1. And our page table entries now, if you are the root of the tree, we call it a directory. And the entry doesn't tell you the frame number now. You use some bits to identify where is the next page table in your chain of trying to find the frame number. So now we are mapping a page number to the address of the next level's page table. And then the final level, the page number finally will map to a frame number. And again, we are never making parts of this tree that have no valid entries in them. Excuse me. All right. So let's take our example from before. So we have a single level page table. This is process A. There are 16 entries in this page table. And of those 16 entries, 7 are valid. So less than 50% of the entries in that page table are invalid, which means we're wasting about half the space. All right, let's turn it into 2 levels, just 2 levels, and see what happens. So I'm going to use 2 levels. So instead of what I'm going to do is, instead of using 4 bits for the page number, I'm going to use 2 bits for the first page number and 2 bits for the second page number. We'll get into how you can compute that in a bit, but not right now. So I have my directory. That's the root of the tree. And what I know is that I only have valid entries, since each one can now only index by only 2 bits. I can only have 4 entries in each table. So I have, my first table is the original 1, 2, 3, and 4. And then my second page table will contain 4, 5, 6, and 7. And so from the directory, page 0 points to a valid table, that's table 1. And page 2 points to a valid table, that's table 2. But I have no valid entries for pages 2 or 3, and so I don't even make that part of the tree. They would all be invalid anyway, so I didn't need them. So I don't create those subtables. And then when I index into those other tables, now I actually have the frame numbers. Now, how many invalid entries are there in total in my 2-level table? Well, there's 1, 2, 3. Just 3 invalid entries. How many total page table entries are there? There's only 12. So by dividing this one into 2 levels, I went from 16 entries to 12, and I went from 9 invalid to 3 invalid. That's pretty awesome. Now, some of you might be sitting there thinking, well, what if I am using every single entry in the address space? Is multi-level paging going to save you any memory? No, it's not. So this is kind of taking advantage of the fact that we often use significantly more bits to address virtual memory than any process would ever actually use. If there was a process that truly did use every single frame of virtual memory, then technically speaking, the multi-level page table would be significantly bigger than the single level one. But that doesn't happen in practice. And in fact, multi-level paging is exactly what the computers sitting in front of you are doing right now. And I believe most of them are using 4 levels to do it. All right. How does address translation work then? Well, this is a fun one. In order to do the address translation, we have several bits set aside for each of the different levels of the table. So instead of a 2-part address where we have page number, page offset, we now have a multi-part address. We still have a page offset, and the page offset doesn't change. Page offset is only ever related to the page size, and if we didn't change the page size, which we shouldn't change the page size, then the page offset stays the same. The other parts, instead of having just one page number now we'll have a bunch of page numbers. However many levels there are, that's how many page numbers there will be. So in our 2-level tree here, we have 2 page numbers. So we are using, just for the sake of discussion, 2 bits to index the directory. So we go to the directory, we use 0, 1. I'll get the entry for 0, 1. If it is valid, it doesn't give me a frame number, it gives me the address of the next level page table. And then I get that page table, and I pull down the next page number. And I use the next page number to index that next page table. And since it's only 2 levels, we get the frame number. And then actually what's really interesting about multi-level paging is once you have the frame number, the address translation is the same. Frame number times page size plus offset. Drop the frame number into the higher bits, drop the offset down, and you're done. The only thing that changes with multi-level paging is the fact that it takes a little bit more effort to actually get the frame number now. So you have to follow a chain of things. All right. So here's kind of the format of our address then. So as I said, you're going to have a multi-part address with some number of page numbers that is going to be equal to the number of levels you have in your multi-level page or your tree. And then you have the offset. Now what we're going to do is, it's a little bit more complicated to actually get to the frame number. So you get the first bit, and as I said, you're going to use that to index the first level tree, the directory. Don't look at the address yet. You must always check that valid bit first. You check the valid bit. If the valid bit is 1, then grab the address to the next level. But if the valid bit is 0, then you throw the exception immediately because there's nothing there. And you have to check that valid bit at every level, always. So we could be throwing an exception off of the directory, we could be throwing an exception off the middle of the tree, and off the very end of the tree. Exceptions will be thrown at each and every stage. Okay. All right. So, some fun stuff. One of the goals we have, of course, in multi-level paging is we want to, in general, reduce the size of the page table that we're storing in memory, because that's actually part of the kernel's memory, and we want to keep that as small as possible. And so, one of the goals that we actually have, and this may not make sense to you at first, but it will make some sense to you as we go along with this module, is that we actually want each individual page table, so the directory, each subtable, we want each of those subtables to fit in exactly one page. I want no table to be bigger than a page. Why? Well, because of things like on-demand paging, it's very convenient if when I need to go get something for a page table and that page table is not in memory, I'd like to only have to do one read from my disk. So for performance sakes, we like our page tables to fit in exactly one page. This is not true for single level paging, this is only for multi-level paging. All right. So, given that fact, we can now figure out exactly how many levels we're going to need in order to create our multi-level tree. So, worked out just fine, by the way, for our example in the slides, but we have another example here. So let's suppose you're using a 40-bit virtual address. 40 bits, that's not bad. And so we actually have 2 to the power of 28 pages. Okay. That's a lot. How many of those pages, or how many page table entries can you actually fit onto a page? That is something that we actually have to take into consideration. How many page table entries can you fit on a page? Because that is going to help us in calculating how many levels we need. So if we make the assumption that each page table entry is 4 bytes, then we can fit 2 to the power of 10 page table entries on a page. Now, how did I figure that out? Well, we take the size of a page and we divide it by the size of a page table entry. And that tells me exactly how many page table entries will fit on that page. So I can fit 2 to the power of 10. Okay, that's not bad. All right. So then, if I can fit 2 to the power of 10 on a single page, then I would need 2 to the power of 18 page tables. How did I figure that out? Well, I have 2 to the power of 28 entries, 2 to the 10 per page, so I have 2 to the power of 18 individual page tables. And therefore, 2 levels isn't going to cut it. Because if I did just use 2 levels like we were using in the slides, then what's going to end up happening is, sure, each of my individual tables that can store the frame number are 4 kilobytes in size, but my directory would actually be over a megabyte. So what we have to do is we say, okay, well, let's keep dividing, and let's keep dividing until we figure out exactly how many levels we need to keep that true, that each table fits on exactly one page. Now, interestingly enough, you can't have any table bigger than a page, but we will allow you to have a table smaller than a page, because obviously that's okay. There's not a problem there. We'll just use fewer bits to index it, and it takes less space on the disk. Now, I have a bunch of formulas, and I would normally use this opportunity right now to go through those formulas with you, but I think I'm going to save that for Thursday's class. And what I'd like to do is, you've seen single level paging and multi-level paging. You've had some time to process it. So I have a handout here. I know we haven't done one in a while. This one's on single paging. And why don't you take the next 5 minutes or so, and again, you can work together, and you can do this, and I'll make sure this gets posted to Piazza as well. Don't use a calculator, okay? I know it's tempting, but you've got to get into the practice of doing hex math without one for the exam. Unless you somehow manage to put one under your skin, in which case I'm not sure how we'd ask you to remove it.
I get it conceptually. Yeah, I just don't, yeah. Then you're good to do this. Do it. Expect to know my next.
The only description was the you
Also, it says, what are you talking about?
So the only person has something to do with the
Yeah. It's not possible.
All right, so you're gonna pull that coming that way.
It's not going to hold up. It's not going to hold up.
Is there anyone that did not get one?
This is the exact same thing.
At least how do you know? Oh yeah, no. How do you figure out? Oh, okay, some of the you only use the 128 kilobytes. That's all right. 4 kilobytes. Sounds right. I know usually you actually kind of tell when it goes based on the light That's the same
That's like the most easy of things that we
Yeah, that's fair. That way you can write down the same thing and you get at least one mark. Get a multiple choice test of the concept.
I hate that. Also, actually wrong on purpose because I feel like they should all be A.
And you question on the mix of averages.
How
I think we the first I have no idea.
Alright. So, this is a fairly standard machine that we've created on this paper. It is 32-bit virtual and physical. Hey, it's just like OS 161 and Windows circa 1990 and so on and so forth. And we're also using a 4 kilobyte page size. Again, very, very standard. This is a boring problem. They get more fun, don't worry. So the first question is asking, what's the total number of entries in the processes page table? Anyone know? I heard someone say 2 to the 20. That is exactly right. Remember that for single level paging, you have an entry for every page regardless of whether you're using it or not. So, for question 1, it is 2 to the 20, and that is because we have 2 to the 32 bytes of memory divided by the size of the page gives us 2 to the 20 pages. And we have 1 PTE per page. Yeah. All right. The next question, though, is how many of the entries in that page table are valid?
32.
It's 32. Now, how do we arrive at that? So for question 2, we have 128 kilobytes address space. Now, this is making the assumption that it's a contiguously allocated address space, which we all know is a total farce, but anyways. How do we figure out how many valid pages? Well, how many times can you fit 4 kilobytes into 128? So we divide that by 4 kilobytes, and you get 32 valid. Not bad, right? All right. Then we have a whole problem that's asking about the physical addresses that correspond to each of the virtual ones provided. Now, I'm not going to pull these out of you. So the first one is, I just got to make sure I'm counting all my zeros properly. There you go, that's the first one. It is valid. And in fact, what's nice about this particular problem is all the addresses are valid, right? That's great. We like valid addresses. The second one is going to be 234 FB5. And the last one, ooh, that's a fun one. The last one is an interesting quirk of virtual memory. It just so happens that that page maps to the same frame number. And so the virtual address and the physical address are actually the same. That's kind of fun. Does anyone disagree with these values? question then says, if we changed the page size to 16 kilobytes, how would that affect the number of entries in the page table? And in the interest of time, how we do this is we repeat the first problem, except instead of using 2 to the power of 12, now we use 2 to the power of 14. So you end up with, for the last question, you have 2 to the 32 divided by 2 to the 14. So you have 2 to the power of 18 entries. And we'll leave it there. I'll let you figure out how many bits we then need for the page number and the page offset. Now before you go, please remember that I've had to cancel my office hours today. I know that's probably a bit of an inconvenience for you. I will be online actively answering your questions, so go from there.